I remember the first outage I caused. I was a junior engineer fresh out of university, and I pushed a database migration that locked the entire orders table for 2 hours. The company lost thousands in revenue. The weird part? The migration script was reviewed and approved by two senior engineers. The failure wasn't in the code, it was in the process. The boring, invisible safeguards that nobody thought to check. Most outages look like that. In 2017, a typo in a single command took down a massive chunk of the internet. It wasn't a hack. It wasn't a DDoS. It was a mistyped argument during routine maintenance. The thing that really breaks your system isn't the dramatic, unpredictable catastrophe. It's the small, boring thing you didn't test. Here's what's actually happening. Every complex system runs on a set of assumptions. You assume your load balancer will fail over gracefully. You assume your database connection pool won't exhaust. You assume that a config change pushed at 2 a.m. won't cascade into a full-blown outage. And when those assumptions are wrong, you don't usually find out until it's too late. The mechanism that causes large-scale failures is almost always a cascade. A tiny local failure escalates because the system lacks the safeguards to stop it. Think about your own stack. You've got a service that handles payments. If it can't reach the payment gateway, what happens? Does it retry? If it retries, are the retries idempotent, meaning a duplicate request doesn't charge the customer twice? If you don't know the answer, you're already one misconfiguration away from a very expensive incident. Idempotency is one of those boring safeguards. It's the property that ensures an operation, when repeated, produces the same result. In payments, it's the difference between a double charge and a simple retry. In event processing, it's the difference between duplicate data and a clean pipeline. Another safeguard is the circuit breaker pattern. If a downstream service starts failing, a circuit breaker stops your system from hammering it with requests that will only make it worse. Instead, it fails fast and gives the struggling service room to recover. Without it, you get cascading failures. One service goes down, then the next, then the one that depends on that, until your entire platform is unresponsive. Now here's the counterintuitive part. The systems that seem most reliable are often the most fragile. If a service never breaks, you probably haven't tested its failure modes. You don't know what happens when a read replica lags by 30 seconds, or when a cache node goes cold. You've built a system that works perfectly in the happy path, but you haven't designed for the unhappy path. This is where chaos engineering comes in. Netflix pioneered this with their Chaos Monkey tool, which randomly terminates instances in production to force engineers to build resilience. Their insight was that the only way to trust a system is to constantly challenge its assumptions. Real-world proof is everywhere. In 2012, Knight Capital lost $440 million in 45 minutes because a new trading algorithm was deployed without proper testing, and an old, unused code path was accidentally activated. The code was reviewed, but nobody tested the edge case. The post-mortem revealed that the real failure was a missing kill switch, a simple mechanism that could have stopped the runaway trades. In 2017, the AWS S3 outage was caused by a command line typo during a routine debugging session. It took down services like Slack, Trello, and Quora for hours. The underlying issue wasn't just human error. It was that the system didn't have enough safeguards to prevent a single mistyped command from having global impact. At Xentro, we process millions of tracking events daily for our clients. One of the first things we built was an idempotent ingestion layer. Every event carries a unique key, and the pipeline automatically deduplicates. That single design choice has prevented countless data integrity issues. And it's a boring, invisible layer that nobody ever notices until it's missing. So the next time you're pushing a config change or reviewing a pull request, ask yourself, what's the boring thing I'm not testing? What's the kill switch that doesn't exist? What's the assumption that's never been challenged? Because the outage that takes down your platform probably won't be the big, dramatic one. It'll be the single line of config that nobody thought to check.